Hello everyone. Today we are going to see the problem convert sorted list to BST. So, given the head of a singly linked list where elements are sorted in ascending order, convert it to a height balanced binary search tree. So in the example we have been given this linked list. So let us try to form some possible binary search trees from this one, okay? So we can have this one, or we can have this one, we can have this one, we can have this one. We can have many more, okay? So in the question, we have been given that our tree should be balanced. Now, what does it mean? A balanced binary search tree is a tree in which all the leaf nodes in the left and the right subtree are in the same level or at max one level lesser or greater. What do I mean by that? The height of this left subtree is 3, right? And for the right subtree as well, the height is 3. So both the height are 3 and 3, so it's same, so it's balanced. Or even if it's say one side is 3 and one side is uh, let's say 4, okay? So that would also be a case of balanced, but as soon as the height increases more, okay, uh, let's say this is the height now, it becomes, let's say, 5, okay? So in that case it won't be a balanced tree, okay? So in case of a balanced tree, both the height of the left and right subtree should be, the difference of their height should be either 0 or at max 1, okay? So that is a balanced tree. So since we are supposed to form balanced trees, then this tree and this tree directly get eliminated, right? Because they don't have, they lack one of the subtrees, right? This one has a right subtree but this doesn't have a left subtree. This one has a left but doesn't have a right, so this is not at all a balanced tree, okay? So they are discarded. These are the ones, okay? Let's say this is our given sorted list, okay? Now let's create a balanced tree from this one, balanced binary search tree. It would be, so this is going to be the balanced binary search tree for this given sorted list, okay? If you do a in order traversal of this tree, you are going to get this sequence, okay? Let's verify once. Left, root, right, 2 3, this left turn, root, now right, this right, left, root, right, 5 6 7, 1 2 3 4 5 6 7, right? Now let us try to make some observations from this tree, okay? So this is our root. Now this root, where does it lie in the list? It lies here. It's the middle of the linked list, okay? Fine. So if this is the middle, this is the left subtree and this is going to be the right subtree, okay? Now let's look at the left subtree. What is the root of the left subtree? It's 2, this one. That is, in this half, the middle node is going to be the root for this subtree. Now let's check the right. In this, the head is, the root node is 6, that is middle of the right subtree, right sublist, right? And then it further gets divided into more parts, okay? So for this one, this is the left subtree, this is the right subtree, this is the left subtree, this is the right subtree for this 6, right? And at the end, when they become leaf nodes, they are itself the root nodes, right? For their uh, children below, which don't exist, right? So this is an observation. We are going to find the middle of our linked list, okay? That is going to be our primary root node of our tree. Now after finding that, we are going to divide our tree into two halves, one left half at the left and another right half. Now in that left half, we are again going to find the middle, that is going to be the root node of our left half, and in the right, the middle node is going to be the root node of our right half. So can we see a recursive fashion here? We can. We are recursively going to break this list down into single nodes, okay? And at each step we are going to find the middle and we are going to assign them as the root node, then again divide them both their sides, okay? Now there is a thing, since we are going to divide this two, right, we are breaking them down, right? So this is going to be the left and this is going to be the right. Now we can see that this 3 is connected to 4, okay? If we keep this connected, then it's going to cause us a problem, okay? We are breaking it down, we have to break this link, okay? Because this Root node is supposed to point to the left. The left is not supposed to point to the root, right? This is the direction, isn't it? This is not the direction, so we have to break this link. Okay, but this at this side it's fine. Okay, so we will see that. So what is our algorithm? Find the middle. Okay, then break it down to its left and right half. Then again we are going to find the middle in this one. Okay, then again going to break it into left and right, left and right. Okay, and while we are finding the mid, we are going to make this mid as the root node at each step. Okay, before going down. So this mid is going to be the root. Okay, now when we in the left subtree, when we find the mid, that mid is going to be the root. Okay, in the right subtree, the mid is going to be root for this one, this part. Then we break them down. Whatever list is remaining here, we are going to find mid again, that is going to be the root here. Similarly root, root. Okay, so recursively we are going to do that. Now there might be a question that how do we find the middle of the linked list? Okay, one easy way or the naive way is to traverse through the list, whole list, and find the length. Okay, now where is the middle node going to lie? It's going to lie at the n by 2 position, isn't it? By 2 position. So we are going to we can reach up to that n by 2 and find our middle node, but it's going to make us do 2 traversals. But there is a better way. I hope all of you know that. We are going to take the help of slow and fast pointers. Okay, very easy thing. There is a question also. Fast is going to be here, slow is going to be here. Fast is going to move by 2 steps, slow is going to move by 1 step. Fast moves by 2 steps, slow moves by 1 step. Fast moves by 2 steps and slow moves by 1 step. Okay, now whenever fast reaches a position like this, either the next is null or the fast is itself null. Okay, then that means our fast has traversed the whole list and our slow is lying at the middle. Okay, because if fast is taking 2 steps, slow is taking 1 step, that is slow is traveling half of the distance, right? So when fast travels the full distance, then slow will travel full by 2 distance, isn't it? Easy thing, right? So that's how we are going to find the middle. Now let us quickly write the code. Okay, we'll see the rest of the things on the go. Okay, if our head is null, that means if our list is empty, then we have nothing to do. Simply return null. Okay, otherwise let's say in our linked list we have only one node. Okay, in that case the next node of the head is going to be a null, isn't it? So in that case return that node itself as a tree node. Return new tree node head dot val. Okay, here our task begins. We have to find the mid. Find mid head, right? Okay, before anything else, let's quickly write how to find the mid. Okay, private list node find mid list node head. We need slow and fast pointers. List node slow starts from head, also fast it starts from head. Now we are going to need one more pointer, slow previous. Let's say why, let's see at the end slow is going to lie here, right? And fast is going to lie here, and we have to break this link. So in order to break this link, we have to have a reference at this node, right? Let's call it slow previous. So our when slow previous reaches here, finally after finding mid, our loop is going to break, and after that we are going to assign slow previous next as null. Okay, we will break this link, we will disconnect from this slow. So that's why we are going to use slow previous. Okay, while fast is not null and fast's next is also not null in bounds, right? First put slow previous as slow. Why? Let's say we start from here, slow and fast. Slow previous is lying here. Okay, so before moving slow here, let's assign this one as the slow previous. Okay, then let us move slow here, isn't it? Otherwise if slow moves here before assigning slow previous, we will lose this node, isn't it? So slow previous equals to slow. Now slow moves to the next node. Slow equals to slow dot next, and fast moves by 2 steps. Next dot next, right? Finally, at the end, after this loop breaks, fast will either reach here or it will be out of bounds. Okay, so that's when the loop ends. We will set slow previous dot next as null. Okay, and we will return slow. What is slow? Slow is the mid, isn't it? Okay, so this will return the mid. Now what to do? Since we have found the mid, let's make it as the root. Okay, t node root, new t node mid dot val, right? Okay, we created the root. Now we have to create the left and right halves, right? So root dot left equals to, we will recursively call this function on it. What is it? It's going to be head. Root dot right, it's going to be mid dot next. Why? Let's see. So we are here. We have broken it. Okay, broke the link, and we are here. So for the right half, what is going to be the beginning of our right half? It's going to be slow dot next, isn't it? For this right half, what is going to be the beginning? This one, that is next of slow, isn't it? That's why slow dot next or mid dot next. But what about this one? What is the beginning of this list? The beginning of this list is nothing but the head itself, isn't it? So that's why for the left half we are calling the function on our head. Okay, after finally building our tree down below recursively, when our tree is finally built, we will simply return the root. Okay, so this is our simple solution. Let's try to run it. Let's submit. Cool. Now what is the time complexity? Let's see. We are building a tree, right? And the height of our tree is going to be a log of n, isn't it? A height of a binary search tree is log of n, isn't it? So our operation is going to continue till log of n time. Okay, and at each step we are computing the mid, isn't it? How are we computing the mid? We are traversing the whole list, not the whole list, the part of the list, isn't it? So that can be at max n. So at each step we are doing our n operation, isn't it? So log n into n, which is nothing but n log n. So our time complexity is going to be O of n log n. Okay, the log n to build the tree and the n to find the mid at each step, log n times. Okay, when finally this height is achieved, our building will stop. Okay, that's why log n time. We are building this height actually. Okay, now what about the space complexity? The space complexity is going to be a log of n. This is the recursive stack space. Okay, so this is all about this problem. Okay, this find mid part, what are we doing? We are finding the mid of the linked list, right? There exists a question itself, okay, on lead code to find the middle of the linked list. You can definitely try it out. Okay, if you have any doubt in this one. So yeah, that's all. If you like this video, do hit the like button, share this video and subscribe to my channel, and I will see you in the next video. Bye bye.